Good afternoon. Welcome back from lunch break. All our friends abroad are also back to this next session of our program, which is the second session. This session will be moderated by Dr. Castel Jean Carlos and Mr. Orlo Elton. We are honored to have Dr. Castel with us here. He will moderate from the main hall from here. I'm sure also Mr. Elton is online. Dr. Castel is the incoming vice president of the elected vice president of IULTCS. He has rich experience, more than 40 years, 45 years in the laser industry, worked in big chemical industries like TFL, Star, currently working for a big biotech company in USA. They are providing biochemicals from probiotics to laser and laser other industries. Mr. Elton is also manager, laser strategic marketing at Bachman Laboratory, USA. They will introduce to us the details of the presenters and the topics of the presentation briefly. I will leave that to the moderators. Allow me, therefore, to leave the floor to Dr. Castel. Over to you, Doc. Thank you very much.
Hello? Can you hear me? Now, yes. Okay, thank you. Okay, thank you so much, Professor, for the introduction, and very welcome to this amazing second session, because we'll be cover several topics that are of very high importance to the leather industry. So we will cover from bean house, that means unhearing, and finishing, that will be something that related with nanotechnology, but also we'll cover about biodegradability, and really one excited presentation, because I want to know really, I mean, how can we use the residuals of the leather industry on the solar panels? So that will be very, very, very exciting presentation. So Elton, if you can introduce the first speaker, please. Seems they are claiming they cannot hear us.
Okay, thank you. Sorry about that, but I couldn't get off mute there for a minute. It's a distinct pleasure to join this August meeting, and very happy memories of being in Ethiopia in the past. And sorry, I can't join you in person. But very excited to introduce our speakers for this session. And the first speaker will be Dr. Kwang. He's head of the Department of Material and Tanning Engineering at Qilu University of Industry in China. He's a member of the Leather Technical Committee of the China Leather Association. And his interests in research include high-value utilization of functional polymers used in tanning, and also in tannery waste. And today he's going to speak to us on a very interesting topic, and that is on self-cleaning leather. I'm sure something that would be useful for all. So over to Dr. Kwang.
Thanks. Ladies and gentlemen, Ladies and gentlemen, my topic of the speech is study on construction and the impact of sling clean laser. First of all, please allow me introduce myself. I'm Dr. Kwang from Qinghai University of Technology in China. And my research focus on the polymer material on the laser production. Next, we can see from these two pictures that the waterproof of traditional laser
Okay, I'm still seeing Dr. Kwang's. Actually, there's a GIF or a video that's playing. Okay, sorry about that technical glitch. We will try and get that fixed. In the meantime, it's my distinct pleasure to introduce Carl Flowers. And I think he's also a Rhodes graduate, so that's something we share in common. And he's technical director of Authenticate. He also works with Sustainable Leather Foundation. He's been lecturer at the University of Northampton. He works as consultant and teacher, and he's an eminent leather scientist. And today he's going to talk to us on the very important topic of biodegradability of leathers. So with that, over to you, Carl.
Okay, thanks everybody for attending this conference, and I'll try and get through it in the same sort of time as I did in the pre-recording. The research that I'm going to focus on today is some of the research that our laboratory has been doing on the biodegradability of leathers in general. Before I move from the first slide, you can see a very important team who are very influential in this work. I'd like to say a big thank you to Abby Clare and to Ellie Dring, who are two of the researchers and laboratory technicians on this side, who had done a fantastic job in putting together this research for the conference. Okay, am I back?
Yes, you're back.
The difficulty, I apologize to everybody, the difficulty about these slides is they actually have a pre-recorded message over them. So as I'm talking to you, I'm also hearing myself talk, which obviously you can't hear. Anyway, this particular slide shows that this is the area of focus that our laboratory does. We work in sustainability leather, obviously linked to the ecosystems and the way that leather interacts with that ecosystem. But in particular, we're extremely interested in the circular bioeconomy, which I've spoken about before. In general, this is the abstract of what the work that we did here. We took fully biodegradable tanned leather and we retanned it with various treatments. We then took 3 treatments to that fully biodegradable tanned leather, and we added different retanning agents. We added more zeolite to one treatment. We took a phenolic syntan to another treatment, and we took a polyphenol, and we added that as a retannage. So the only difference between those particular leathers were the types of retannage that we'd done. We had kept the dyeing and the fat liquoring absolutely identical. Of course, all the pre-treatments, the beam house and the preparation for tannage was the same. Let's just go back one slide to finish on here. So in terms of the results that we got, we did see that in general, the biodegradability of the leather decreases when we add complexity to the retannage. So as we increase aromaticity of the retannage, or whether the interaction between the chemical itself and the collagen complexity increases, we tended to see a decrease in the biodegradability of those leathers, of those treatments. Oh. This is a nightmare. So in terms of some background, what is very important to think about in terms of biodegradability, it's important to think about where you are considering that biodegradability, in what biome you are trying to assess that biodegradability. And what we do know is that in environments where there is a lack of oxygen, the biodegradability is much more complex than, say, for example, a biome where you have the presence of oxygen, aerobic biomes, for example, composting, or in a terrestrial biome. Another very important consideration is, of course, whether the material that you're trying to consider is going to go through a composting process. It's also important to recognize that in the European Union and in the North America, there is a real desire to increase the amount of recycling of leather and other products. And in terms of composting, the European Union specifically identifies composting as a recycling method. So for the brands and companies who are listening here today to gain some insights on biodegradability, one of the messages that you can take away is that if you do adopt a compostability approach, you will be meeting some of the recycling aims of the European Union. The European Union identifies, as I said, composting as a recycling method. It only identifies disposal of materials as either landfill or incineration. It does not recognize composting as a disposal method in terms of the waste directive. Of course, it's also important to recognize that currently there is only one leather biodegradability specific test. In other words, a scope which includes leather in its remit, and that is the test for ultimate biodegradability in aqueous environments, ISO 20136. So where could biodegradation take place? And this particular slide shows a whole range of different biomes where biodegradability could take place. And you have to test these materials in all of these different biomes. On the left-hand side, you can see landfill, which is an anaerobic biome. In the middle, there's a whole range of aerobic biomes, including in composting, industrial and home composting processes. And on the right-hand side is the areas that I'm going to focus on today. That is the aqueous or marine environments, which are comprised largely the rivers or the marine environment where you can see that plastic bag floating. Of course, if these materials float to the fringe of these biomes, say, for example, inside the sediments or on the shorelines of these bodies, you then get these sort of marginal biomes where a number of different things can take place. But the aqueous biodegradability test that I'm going to show you today, ISO 20136, focuses on the aquatic environment, obviously not the marine environment, which includes salt. So in terms of the materials and methods, we took a cattle hide of German origin, and this trial was done in Germany. We divided the hide into quarters, designated those quarters using a random Latin square, labeled them, and prepared the material for a zeolite tannage, and then, of course, used a zeolite tannage as per recommendations by the supplier. We also took a separate material as a collagen control. This was proprietary hide powder, which was predominantly collagen type 3, and that was the source of our collagen control. The four next chemistries that you can see there, that is a material that was only semi-processed. In other words, it was just tanned with no retannage. A separate treatment on another quarter was the zeolite with the zeolite tannage with the zeolite retannage, and of course dyeing and fat liquoring. A phenolic syntan in place of that zeolite on the second quarter, of course with the same dyeing and fat liquoring. Everything else was standardized except the retannage. And of course the third treatment on a third quarter was a hydrolyzable polyphenol that was put in place of the other retanning agents, of course again with the standardized dye and fat liquor. After the treatments, the material was dried and softened using standard shoe upper techniques. And of course, the final leathers were sent away for carbon content analysis. This is important because we need to understand what the theoretical carbon dioxide that material can produce is capable of. We then followed the ISO 20136 standard method, something that our laboratory does, and followed the standard analysis that you would do for those particular materials. In terms of the results and discussion, you can see here the carbon content shows us a range of different carbon contents. We would expect the dry matter to be in this region, 10 to 15%. And on the left-hand side, you can see a range of carbons. You might be wondering why the zeolite carbon content goes down. Well, obviously, it's an inorganic substrate, and as soon as you introduce inorganics into a carbon background, it dilutes the carbon that's there. As soon as you put the retannage back in, together with a fat liquor and together with a dye, the carbon content goes back up to what you would expect it to be. This is the typical graph that comes out of 20136. You can see that on the left-hand side at the origin, you're not expecting any carbon dioxide to be evolved yet. Our instrument measures carbon dioxide by infrared, and it monitors cumulative carbon dioxide release over time. We remove the background carbon content that could be coming from the activated sludge inoculum that we use, and then we monitor the accumulation of carbon dioxide over time. The gray line is our collagen control. That is the type 3 collagen control that we use, that we know is perfectly biodegradable. And then you can see that the performance of the biodegradability of the various curves decreases as you go over the 28-day test. The green line, of course, is just the semi-processed zeolite tanned material. And then you can see that starting with the blue line, we have the zeolite retannage, followed by the red line, which is a phenolic syntan tannage in place of the zeolite. And then you can see that as we introduce a polyphenol, the complexity of this material increases, and the bacteria, it's very important to recognize that we are dealing with a bacterial environment here, seem to struggle with complex chemistry. If this was a fungal environment, a solid substrate test, we may find a completely different form of biodegradability, because of course fungal species are a little bit more adept at dealing with complex interactions. So we would get a slightly different result if we were dealing with a solid state test compared to the aqueous biodegradability. Chemical people in the room will be familiar with the OECD 301 type of test. It's a slight modification of the 20136 test for chemical substances. You would also appreciate that things get slightly more complex. For the wastewater treatment people in the room, you will also be able to resonate with this. Increasing COD is associated with chemicals that are quite complex to break down in effluent treatment plants. Because bacterial species are responsible for that breakdown, you will see something similar. So this really emulates what we see in industrial wastewater treatment plants. This table shows what we call the absolute biodegradation. On the left-hand side there, the percentage cumulated CO2 out of total CO2 that's possible. And you can see that it pretty much replicates what we see in the graphs, of course, because it's data points that actually come from the graph. Now, on the right-hand side is a curious anomaly of the test method. They do something called the relative biodegradation, where they take the collagen control on the left-hand side there, the absolute biodegradation, 91.59%, and they say, what do you need to do mathematically to make that 100%? And whatever you need to do to that 91.59%, you have to do for all the other absolute biodegradations in your experimental test. So you can see that 74.42, 66.36, and et cetera, has just been modified by the same multiplier. And you can see the numbers of what the relative biodegradation is. Now, what this is supposed to emulate is that what is the level of biodegradation that the samples would undergo if, when the collagen control reaches 100, where would they be relatively speaking? So this is a mathematical exercise. It's a terrible way of doing things, and if you have time later, I would love to tell you what I think is an absolute terrible part of this test. But it does show what the test method requires you to do. I have a better alternative for this, and what I think we should be doing is doing a nonlinear graph extrapolation. But again, we can talk about that a little bit later. So this is the graph.
If you could wrap up in 2 minutes.
Well, no problem. So in conclusion, what we can say is we can say that collagen biodegrades the most in aqueous biomes. Obviously, we know that it's very biodegradable. We then know that if you just take a material that is collagen-based, tan it with something like a zeolite, we know that it biodegrades slightly less than the collagen, but well. And then, of course, we saw the hierarchy. We saw that just a straight zeolite retannage gave you slightly higher biodegradability than a phenolic syntan, which was a slightly higher biodegradability than the polyphenol. And what we can conclude is that chemical complexity of your retannage increases the problems that the microbes have to face when coming to a aqueous biodegradability. It's very important to recognize that this would be slightly different in a composting or solid state environment. So it's not fair to grade those retanning agents as good, bad, or other in that particular case. The references that we used were what's listed here. And finally, I would just like to acknowledge the organizers of the conference and the sponsors of the conference. Thank you very much for that. A second thank you to my team. And I would just like to disclose that this research was funded by our organization and that there were no conflicts of interest. Big thank you to BLC Eurofins, who supplied us with the biodegradability, the inoculum for the 2136 test from their effluent treatment plant. Thank you very much.
Thank you, Carl. As you're aware, we'll hold questions till the end of all presentations. Very interesting presentation on biodegradability, which is becoming increasingly important for our industry. With pleasure, I want to introduce the next speaker, Mr. Julian Osgood. He's a graduate of University of Northampton. He's worked in industry. He's worked for some chemical supply companies, currently with ATC. And he's going to talk a little bit about traditional hair removal versus hair saving process and compare these systems. So with that, we'll pass it over to Julian.
Together with Emmanuel Hervey, today we would like to present to the IULTCS Congress Unhearing System Comparisons. Today we would like to compare a traditional hair burn process using sodium sulfide against a zero sulfide process that we have developed. Unhearing principles, traditional hair removal process. In the conventional liming hair burn process, the liming chemicals either destroy the hair and epidermis completely, or they loosen them to such an extent that they can be removed mechanically. This process traditionally uses around 1.5% to 3% of sodium sulfide and sodium hydrosulfide. Compare this to the hair saving process. The hair save process uses the same chemicals as the hair burning system, that's lime and sulfide, but we apply them differently. The principle of the method is the hair fiber is firstly partially protected by lime and then enzymes added with a low or even a no sulfide process to attack the hair roots, thus allowing the hair to be removed by a filtration and collection process. This process can use zero sulfide, or if a part process is used, up to 1% sulfide. What are the advantages of using a hair saving process? Firstly, a lower TDS, a lower total dissolved solid content of the effluent. With this, you have a high volume of solid waste suitable for processing into saleable byproducts. By this we mean the hair is actually collected during the process rather than being dissolved into the effluent and needing further effluent treatment processes. Because of this, we get a much lower BOD and COD and nitrogen content within the effluent. This gives us lower hazardous and unpleasant air emissions within the beam house processes and a reduction in effluent treatment costs. Together with this, we have a reduced sludge disposal costs, reduced sulfide consumption, and therefore reduced hazardous chemicals within the tannery. Let's take a look at the zero sulfide process formulation. We start with a 150% float and a small amount of soaking agent, very typical. Run for a couple of hours, drain, a slightly shorter float for the next process with soaking agents, degreasing agents, emulsifiers and some small amount of bactericide. Run that for 90 minutes and then leave overnight. After draining in the morning, an even shorter float is used for the first part of the unhairing process, where we introduce chemical A. The characteristics of this chemical we're going to discuss shortly. We also add a small amount of lime and we run for an hour. After this, chemical B and C are added and the filtration process is run. In the laboratory scale trials that we did early on, we just used a simple fishing net to fish out the hair from the process at this time. But in production scenario, a installed filtration system could be used at this time. After all the hair has been removed, we add a little bit more water, some more lime, run for 20 minutes and again leave overnight. Draining this the next day, we add another float of 150% water, some degreasing agent, run for an hour, drain and flesh the leathers after unloading the drums. The key points of a zero sulfide process, things that we really have to get right to make the process work. In our experience, perfect wetting back is extremely important. Also, the use of short floats is highly recommended to give enough mechanical action to the process and to use high enzyme concentrations of the products. We need a good immunization of the hairs, a good protection of the hairs, and we need to control the swelling of the hides, not too much and not too little, for the process to work very efficiently. The zero sulfide process key products include chemical A. The characteristics of this product are that it improves lime solubility, it reduces excess swelling, reduces wrinkles on the hides, and it increases the total area of the hides. It gives soft and fine grain. Chemical B is an unhairing enzyme which acts at a high pH and it's designed to attack the hair keratin. Chemical C is an inorganic sulfide-free ecological unhairing agent. It also reduces wrinkles on the hides and improves grain smoothness. This photograph has been taken round about 1 or 1.5 hours into the unhairing part of the hair saving process. These 3 photographs show the unhairing process after running overnight. It's clearly visible from the photographs how the hair remains intact and should be easily removable by a filtration system. Please also note the colour of the float that remains in the liquor. It's much lighter and less contaminated by what would be dissolved hair in a traditional hair burn process. I would like to now show you a short video that Emmanuel and I made as a side-by-side comparison between a sulfide traditional system, hair burn system, and our ZSP system. These two photographs were taken after the process had been running for 2 hours. On the left we see the traditional sulfide hair dissolve system, and on the right the hair saving system. Look at the differences between the two floats. This photograph clearly shows the two hides after the processes. On the left, the traditional hair dissolve method, much darker and more wrinkled than the hide on the right, showing the zero hair sulfide process, which is much smoother and much lighter in colour. This photograph shows the final floats of each process, and I think is fairly self-explanatory. Float samples were analysed from each process, and here are the results. You can see that with the ZSP system, we experienced a total dissolved solids minus 41%, COD was down to minus 47%, BOD minus 14%, and the ratio between the two, BOD-COD, minus 37%. And the sulfide found within the two processes, 110 compared to 0.8 milligrams per litre with the ZSP system. Significant improvement. One of the problems with the system, of course, is removing the hair. This would need a significant investment from the tannery for each drum to be used. And a system something like this could be set up. These photographs show float collecting gutters installed onto drums and hair filtration and collection systems that can be used. I hope you agree that this is a very interesting subject, and should you have any questions, please address them to myself or Emmanuel, or feel free to contact us directly at any time in the future should you need any more information about our project. Thank you very much.
Emmanuel, thank you very much for that presentation. It's a good demonstration of technology in practice. And sorry for the confusion regarding presenter in the beginning.